Okay, so imagine the speed up you'd get training a neural net if you're only training, say, 50% or 30% of the weights. That's what we're going to do here today. This was an experiment that I came up with. It's kind of like, turns out it's kind of like sparse training, except that in sparse training they set all the weights that they're not training, they set to zero. I've not tested versus that to see if there's a difference between the two or what, but we're just gonna go through the code on this. Okay, so first off, we are just creating a new version of the image neural net, and we're just gonna right here create a new class that is, instead of a dense class, it's gonna be, I don't know why I called it fewopt, but a new layer that will be training only a subset of the weights. And I'm not gonna go through coding it out. Instead, I'm just gonna go through and show how it works as I've coded it out before. So I would copy and paste the image neural net, and we'll start from there. So if you start from there, we'll add this function right here onto it. It gets the subset of weights that of the neural net, or of the layer that we are going to want to train. So it is a way of masking all the rest of the weights, so that we can just train the ones we want. We'll do a vector of tuple int, and that's because one tuple of ints, of the two ints, is going to be the location of a weight. So we want a vector of them in order to select all the different weights that we do want to train. Number of weights changed is going to be, I hate that all these pop-ups come up. Don't know how to get rid of them quite yet. I have not looked into it either, but yeah. So we're going to, it's going to be an integer percent. Let's see, what is percent? So we put in the percent into the function, percent of weights that we want to train, and then the number of inputs and the number of outputs, because that multiplying number of inputs and number of outputs gets the total parameter count, times the percentage is going to get a parameter count that, let's say our percent is 50%, you have 100, let's say it's 10 by 10, you'd have 100 parameters, 50% of that would be 50. We make sure this rounds to an integer. And then we'll go through number of weights, and we'll make random number generated through the inputs to be as the row, the random row we're going to select, and column to be the random column that we select. We'll place back into the randvex that tuple. and then we'll sort them from low to high in order to, let's see, we're should be sorting by the 0th tuple, which gets it so that you have each row. You have like the first ones are the 0th row, and then you move on to the first row, second row, and so on. That just speeds up performance during the training. If you basically so that things are in cache. If you do all of the 0th row ones first, those are likely to be in cache. Whereas if you go from 0th row and then next to 6th row and then back to first row, you're likely to have a lot of cache misses. So this just speeds it up. Returns the random vectors. Let's see what we got next. So all the usual stuff here. That's the usual stuff. Here we're going to set, we're going to have 3 layers, and we need a vector for each of those layers of the weights that we want to update. So create those. We will set them equal to each of the I guess the functions that we just made. Pass in the functions we just made to set them using the proper sizes, the %, and then the inputs, outputs of each one. And then we'll make a vector of that will contain all 3 of these. Which I could have done that different. I could have just done a for loop and pushed back each one of these. Instead, I created them and then pushed back. Whatever. You realize the mistakes you make as you go through this. And then, let's see, subset layer is, oh yeah, okay, now I know why this is FewOpt. This is a new optimizer class, is what that is. And let's see. Now I gotta remember where I put this. So subset layer must come from our other file here. Let's see. Usually it would have been our inin folder or file, but in this project I have it as a different name. Let's see here. Let's go find where it's at. Subset layer. Okay. So we created a layer here. A lot of the usual stuff. Oh well, I guess all of this is probably going to be most of it should be exactly the same. We're going to have number inputs, outputs, bias, number of samples. And then we're going to add in the call it randgrads. It is basically these things here. The weights we want to update, the location of the weights we want to update. I guess we should have started here. Yeah, so the weights we'll want to update. You can ignore all the things that say tensor. Sorry. Okay, so we'll start here. That all all the usual stuff. %rand. What is randomize? Oh, you can ignore that as well. But yeah, you can type all this in. Anything that says tensor, ignore. And ignore that one. And then all the usual stuff with the addition of fewgrads, which we're going to copy that randgrads into fewgrads so we can use it on the backward pass. And then I was showing you this one. It's all the same. Yeah, it's all the same. You just add in the fewgrads equals randgrads. All right, the forward will also be just normal, all the same. And then the backward will be where we are different. So backward takes the d values as usual. Delete this. You'll fill d weights with 0. And then we're going to go through the fewgrads. For loop through both of those. Yeah, so it'll go through every each tuple in the vector of tuples is what this for loop does. And then within that, let's see here. Within that, we will go through the rows of the layer inputs and update the derivative of the weights from the layer inputs and the d values that correspond to the row and column of the tuples. So derivative of the weights, row and column equals layer inputs. You do have to go through all of the layer input. Let's see, will this be all the layer input rows and all the d value rows in order to because for a single value of the d weights, you trying to think how to say this. This one derivative is calculated using the whole, like each sample, which is the same for the d values. Each sample adds to it, so multiplying each sample and adding, which is just like doing the dot product. And then layer bias, the exact same. Derivative of the inputs, the exact same as usual. So right here is the only change there is. I can delete all this extra space. And yeah, so that updates creates the derivative of the weights only in these select spots. All the rest of the derivatives are 0. We go back to fewgrads, which is the new image neural net file. So yeah, you will replace every layer dense with a subset layer, which does include we made this random weight labels vector that holds each of the layers vectors. So the first layer has random weight label 0 in it. And then I use the layer dense for the other two, I guess. I'll have to switch those out with subset layers as well and see. We can do that in this video as well if we'd like. But we'll start with this. So 0th one, and then down here everything else for now is the same. Add in, instead of our optimizer SGD, we'll do this view optimizer. This clock is just, you can ignore that because that's just clocking to see the speed differences and to see how things are getting optimized. But okay, so we'll come back to this view opt thing, but we'll just go through down here to see what's different, what's the same. Let's see, I believe everything else is the same. Opt. Interesting. Set layer. What is this? Rand. That's not what I want. There we go. And layer. So actually we're going to find out in real time here if doing all these helps. Makes it better or makes it worse. Okay, so we're doing the subset layers. We're using the view opt, which takes in the Randway labels and the learning rate. But yeah, everything else will look the same down here, except the update params takes the usual layer, but also it'll ask which of the Randway labels we're going into, because we passed the Randway labels into here, so did it so that we know which layer we're on. That's the only thing you add there. Now we go back up to this view opt. Let's see where that's at. Okay, so view opt class here. Constructor, which we had, takes in the rand gradients and the learning rate, and we set the learning rate and these gradients here. Okay, so that's why I had his layer dense. Sorry, I'm just didn't even prep for this video. So we got update for the layer dense, and we got an update for the subset layer. We'll try everything out as subset layer, and then I'll move those other ones back to layer dense if this doesn't work so well. And we will find out. Learning rate we'll throw in there, and then the select gradients, which are the chosen gradients for each layer. And then update params for the dense layers. For the dense layer, let's see here. Okay, so this was a mess up. This should just go through everything and update everything as if it's a normal one. Yeah, interesting. So, but yeah, since I'll just comment that out. That's not right. So ignore this one, if you like, for now. We'll just focus on this one. Which, just like when we found the gradients, this is how we are going to update the weights. Go through the selection of tuples, the vector of tuples, which says which gradients or which weights we want to update, and we'll update those weights. This line looks exactly like the usual optimizer updater. You take the weights minus learning rate times the derivatives. So that looks the same. It's just that we're only going through the ones that are in that vector and updating that way. So I'm going to save that. If I did miss anything or anyone's having any problems, let me know. We'll save that. Let's see what happens. And we wait. Okay, so here's the losses. Going down to 0.59, 0.02. So here is the issue, is one issue here. Goes to that and then to this. It doesn't seem to be always going down. So it goes from like 1.35 to 0.77 back up to 1.54. Or this like 0.02 up to 0.49429. So that part is interesting. But let's check an output or a trial afterwards. Let's see. So this first one is this last one, and the prediction predicts that. Second one is the first one. Prediction does predict it. What's the third one? Third one's right here. Third one right there. It does predict it. Very high confidence. So it seems to be working pretty well. Let's see what the timing was. Timing was 9928. So I think that's just under 10 seconds is what that should be. Oh, and okay, so definitely missed something. Percent changeable weights, 50%. And now we can test this against the normal image neural net, which is right here. So 500, checker 100, and try this out, see what this does. It won't have the test numbers like down here, but it'll tell us a loss. So we can compare the loss. I wouldn't compare the final number for sure, just because the numbers up here were not completely consistent. But yeah, 2.4 as the start, and it gets down to 0.7. So weirdly, even if you count like all of these, any of these, it's all lower. It's all definitely lower than this 0.7, which is crazy. And also here's the time, almost 17 seconds versus up here about 10 seconds. So it's barely more than half the time at running 50% of the weights. So I think that's really interesting. Next video I'll show how you do this in self-attention. It will not be a speed up because all I'm doing is using PyTorch to create a mask on the gradients, and so it will not speed things up. It'll actually slow things down because I'm working with PyTorch. One thing I am doing right now is trying to build a transformer in C++, which eventually I'll put into CUDA. And so, yeah, I lost my train of thought. But yeah, both the next video will be done in PyTorch. It will not be faster. It will, but I think it is better in terms of it does have slightly better accuracy with using, I think it's half the weights. And it's not everywhere. It's I'll show you in the video. It's only in select spots. But yeah, it'll be interesting to show you. And once I get Transformer done in C++ and CUDA, then I can apply it to that, and it'll actually be a speed up because I'm able to control that. But yeah.